Today we're going to be talking about intermolecular forces. Intermolecular forces are forces that exist between molecules. So interactions between molecules. And you'll see that I'm starting here with a table of boiling points. And why is that? Like, why start talking about intermolecular forces when I have a table for boiling points? Well, if we think about what boiling is, this will make a lot of sense. When I have particles in the liquid state, let's say water. Okay, so water is in the liquid state. The the molecules are really close to each other. They're constantly interacting, and this whole network is being kind of held together, and we're going to talk about that in a little bit. So there are interactions holding the molecules in a liquid together. But in a gas, these particles are very far apart. So here might be a water, another water might be over here, another water might be over here. They're not interacting with each other at all. So in order to move something from the liquid phase to the gas phase, what you really have to do is you have to put energy in to break these interactions between molecules. And those are intermolecular forces. So boiling point is a good indicator of the strength of intermolecular forces. And I'm going to use an abbreviation here, and I'll use it for kind of the rest of the video. Instead of using the term intermolecular forces, we'll just say IMF. And we're going to be talking about 3 of them today. And we're going to talk about them from the strongest, which is hydrogen bonding, to the weakest, which is London dispersion. And then the middle one is called dipole interactions. And as great as it would be to do them in the order from strongest to weakest, we're actually going to start with the second one because we need to understand that one in order to talk about all the other ones. So let's just review electronegativity. We talked about it last chapter briefly, but electronegativity is how much an element will pull electron density towards itself in a bond. So let's talk about the compound HF. So if I was going to do a Lewis structure, I might do something like this. And that dashed line represents an electron being shared between the hydrogen and the fluorine. But remember that fluorine is the most electronegative atom. So these electrons here are not very well shared. So rather than thinking about it like this, where those electrons are shared pretty equally, yeah, it's just not like that. The fluorine basically pulls the electrons towards itself. And when I do that, what I have is I have this fluorine that's basically gaining electrons. So it's almost like it has a charge. but it doesn't have a full charge because those electrons, these two electrons here, are still being shared. So it's not a full charge, it's a partial charge. And the way that we indicate this is a couple ways. One is with these lowercase Greek letter delta, and this means partial in this context, okay? So I could say that this one has a partial negative charge, and if I look at the other side of this hydrogen atom that has basically lost an electron, it's now just basically a proton sitting there, which means that it should have a partial positive charge. So one end of my molecule has a partial positive, and the other end has a partial negative. And we have a separation of charge. And this separation of charge we call a dipole. And when it's in a bond, we call this a bond dipole. And when it's in a molecule or a compound, we call it a net dipole. So this compound, HF, has a separation of charge within a bond, the bond between the hydrogen and the fluorine. So it has a bond dipole. It also has a net dipole, and we're going to go over how to determine if a compound has a net dipole later, but this one also does. And the dipole in this one, the other way that we will express this, and we'll use this a lot, is we're going to put like a little positive sign there, okay, right next to the positive atom. And then we're going to draw an arrow coming from the positive side, the more electropositive atom, and point it towards the more electronegative atom. So this would be the direction of our bond dipole and also the direction of our net dipole in this case because there's nothing canceling it. So let's consider the boiling point of two compounds, ICl versus Cl2. So I have ICl here. You'll notice that these are going to be very similar compounds. And I have Cl2 over here. The only difference between these is this compound has an iodine and this compound has a chlorine. So, what's the deal here? ICl has a boiling point of 97 degrees versus negative 34 for chlorine. And remember, we said that boiling point is a good indicator of the strength of the intermolecular force. Well, I mean, let's think about what's going on. So in ICl, there is a difference in electronegativity, which I can tell because I have a Falkland being bonded to a non-Falkland. And anytime that I have a Falkland bonded to a non-Falkland, I have a big enough difference in electronegativity that I can have a bond dipole. The other way that I can know is fluorine to anything. Of course, anything but itself, right? Because two fluorine atoms would have the same bond dipole, but fluorine to anything else is going to have a bond dipole. So in this instance here, the iodine and chlorine bonded together, I have a Falkland bonded to a non-Falkland. So I have a bond dipole. So see if you can figure out which direction it's going to go. I'll just wait here for a second and let you think. hopefully you came up with the fact that since chlorine is more electronegative, it's going to have a partial negative charge. And the iodine will have a partial positive charge. Or the other way that I could draw it is like this. So if I have another ICl molecule that comes and lines up this way, where I have the partial positive now on this side and the partial negative on this side, I've got partial positives next to partial negatives, so I can get an interaction between the molecules of ICl. Okay, this is an IMF, right? It's an intermolecular interaction. It's an interaction between two molecules of the same compound. We're going to do of the same compound this year. Maybe in future classes you'll get into between different compounds, but right now we're gonna stick with same compounds. So this is one dipole, the dipole of one molecule interacting with the dipole of another molecule. So this is a dipole-dipole interaction. And if you remember from a couple slides ago, this is the second strongest interaction. Well, what about Cl2? Well, these have the same electronegativity. And since they have the same electronegativity, there's no bond dipole. Which means no dipole-dipole interactions. And just to kind of drive home how strong this dipole-dipole interaction can be, I have this little diagram here from our textbook where I have the ICl molecule, and you can just see you'll get a huge network here of good interactions between the negative side of one thing and the positive side of another thing. And remember, this is 2 dimensions, so this really is happening in 3 dimensions. Things are constantly moving. This is a very strong interaction, which you can tell because 97 is a very high boiling point, right? We consider things that have boiling points like greater than, let's say, room temperature to have high boiling points, and things less than room temperature to have low boiling points. All right, so negative 34 degrees Celsius, that's quite cold. That is a low boiling point. 97 degrees Celsius, that's almost what boiling point of water, that's a high boiling point. So this dipole-dipole interaction is going to make a big difference in the boiling points of these 2 compounds. Okay, so let's consider water versus CO2 versus CF4. And I have the boiling points written down here already. 100 degrees Celsius for water, negative 78.5 degrees Celsius, and negative 127.8 degrees Celsius. And these seem a little weird. And in order to talk about this, I actually need to go quite a bit beyond the Lewis structure. I actually need the correct VSEPR geometry. So I've done that. You should put it in your notes and just make sure that you have it all. And pause the video, write this table out, and then we'll start talking about this. I'll start talking about water. And I'm just going to ask a simple question. Are there any bond dipoles? Can we dipole-dipole? Well, this one is a yes. I have a Falkland, being the oxygen, bonded to the hydrogens. Okay, so I have 2 bond dipoles, and they both point in this direction, where oxygen is more electronegative than hydrogen, so there are bond dipoles. Well, what about CO2? In CO2, yes, there are bond dipoles. And oxygen is a Falkland, and carbon is not, so I've got a Falkland to a non-Falkland, so I have a bond dipole. And the bond dipoles point out. So there's the direction of one dipole, there's the direction of the other dipole. So here's what I want you to do, okay? I want you to grab your fists in front of you, like make your thumbs go opposite directions and kind of put your elbows out straight as far as you can make them, and then try to pull your hand apart. It's kind of a funny thing, right? And when I pull on both sides, what happens is my hand in the middle doesn't move at all. And what that means, I am pulling out on my hands in both directions, in opposite directions. And so, but what's happening is my hand's not moving because the forces are canceling out. And that's what's happening here in CO2. This bond dipole and this bond dipole are working in opposite directions. And those opposite directions are going to cancel each other out. So yes, there are bond dipoles. However, the bond dipoles cancel. And so we get no net dipole. Well, let's think about CF4. Okay, does CF4 have bond dipoles? Well, yes, again. So this is just getting crazy because all three of these have bond dipoles, but they have wildly different boiling points. And CF4 does also have bond dipoles. I've got a Falkland fluorine bonded to a non-Falkland carbon, so yes, there are bond dipoles. But in this one, the molecule is symmetrical. And when the molecule is symmetrical, all bond dipoles cancel out. So we are left with no net dipole. Okay, so because these two have no net dipole, they can't dipole-dipole. So really, water is the only one that can dipole-dipole. So it's going to have the strongest intermolecular forces because it can dipole, whereas the other two can't because they don't have net dipole, which means that shape is really important. And if I ever ask you to determine what should have a higher boiling point between two compounds, well, you're going to have to draw a Lewis structure. Okay? So let's talk about this net dipole thing and how we do it. Are there bond dipoles? Do the bond dipoles point towards the center or exterior of the molecule? So let's take, for example, a compound like BRF3. Okay? Well, the first thing that I'm going to need to do, because shape is important, is I'm going to need a Vesper geometry. So BRF3, when I draw my Lewis structure, looks like this. So this is a steric number 5. Base geometry is trigonal bipyramid. And then my actual geometry is going to be a T-shape. And only after I have my Vesper geometry, can I figure out if I have a net dipole? And here's what I do. So from the Vesper geometry, I ask myself a series of questions. Are there bond dipoles? Yes. In this case, absolutely, there are bond dipoles. Do the bond dipoles point towards the center or the exterior of the molecule? So fluorine is more electronegative, and I'm going to draw in like little bond dipoles here. Okay, so they all go out. Is the molecule symmetrical, or do any of the bond dipoles cancel? Well, when I look at my molecule, it's not symmetrical. However, these two bond dipoles here are pointing 180 degrees apart. So they're pointing in the opposite directions, which means that they're going to cancel each other out. So I'm going to just real quickly erase those. And the only thing that's left is the bond dipole between the bromine and this fluorine here. So nothing's canceling that one. So that bond dipole becomes our net dipole. Okay, which means that BRF3 can dipole-dipole. All right, now a tricky one is something like a seesaw. So let's look at SF4. Okay, so SF4 has, again, if I do my Lewis structure, it is also a steric number 5. So I'm going to skip my base geometry, and I'm just going to go to my correct geometry, which is seesaw. Okay, now this one, it's going to be a little hard to figure out what's going on. Okay, and in order to do that, I'm going to do a little rotation of the molecule. So the first thing that I can see is that there are bond dipoles. They all point out, and that this bond dipole and this bond dipole are going to cancel each other out. So that just leaves these two. So if I rotate this so that I am looking kind of down this. So I'm not going to see this atom or this atom. They're going to be kind of in my field of vision. So here's my sulfur. And then these two fluorines are part of the trigonal planar piece of the trigonal bipyramid. So they are 120 degrees apart. So I'm going to do this with a solid. So they're 120 degrees apart. And they both have these little bond dipoles that go this way. Okay? And each of these little bond dipoles, I could say, like there's my bond dipole. I could think of it as two other bond dipoles, one component that goes down and one component that goes out. Okay? So when I think about that, that means that I have from this bond dipole, I have a component that goes down, and I have a component that goes out, like this. Okay? And then on this side, I have another component that goes down, and then on this side, I have a component that goes out. So the two out components are actually going to cancel each other out, and the two down components are going to combine. So what I'm going to be left with is a net dipole that bisects this angle pointing outward. Okay, and that goes opposite the lone pair. So, and if I go back to my Vesper geometry, where I'm going to need to draw my net dipole, is going to go opposite the lone pair between these two atoms. Okay, so that's how we identify if there is going to be a net dipole. We kind of ask those three questions, and it takes practice. You're just going to have to keep working on it over and over and again until you see it. All right. So both of these have net dipoles, so they can dipole-dipole. So they'd have pretty strong intermolecular forces, we would estimate. All right, we're going to go from the second strongest, which is dipole-dipole, to the absolute weakest, which is London dispersion forces. And these are also called van der Waals interactions. You'll hear that said. Van der, W-H-A-A-L-S. Van der Waals interactions. I call them London dispersion forces, or LDFs for short. And here's the deal with these. Okay, these are about electrons within an atom. Okay, so if I look here at this atom, so hopefully you've identified that this is a helium atom, right? It's got 2 electrons and it's got 2 protons. And the electrons are kind of like constantly moving around and constantly moving around. And there's a non-zero probability that both the electrons could be on one side of the atom, which makes this side of the atom negative and this side positive, because that's the side that the nucleus is on. And so if another atom comes up to this atom when this is the case, what's going to happen is the electrons are going to be attracted to this side, right? Because there's the positive side over here. And so this side would make sense to be kind of more negative. And in order to do that, the electrons can go over here. So now I've set up something where I have a positive side on this side and a negative side on that side. And those two things are going to interact, which is what I'm showing you over here. This is a very, very weak force. It's not very long-lived, and this is called London dispersion forces. And this is all about electrons moving in atoms. Okay? These are always present. In every single compound, these are always present. And the last thing that's really important here is that the strength the strength does something interesting. So the strength of intermolecular forces does change. So let's think about these compounds: F2, Cl2, Br2, and I2. So you'll notice that all of these have no net dipole. Okay, there's no net dipole, which means that they're going to only have London dispersion forces. Okay, and because they have London dispersion forces, we're like, okay, so they're going to have pretty similar boiling points. Well, this one is negative 188. This one's negative 34. This one's 58.8. And this one's 184 degrees Celsius. That's a massive difference. Okay? So clearly, these are van der Waals interactions only. So van der Waals interactions aren't always the same strength. Well, if we think about what's going on here, like if I get like 30 electrons on this side and I have a plus 30 charge and 30 electrons on this side and a plus 30 charge on this side, this interaction can actually get really very strong, and it does. So the strength increases with number of electrons. And since we're not going to sit there and go like, all right, so fluorine's got like what, 9 electrons, so that's 18 total electrons. And no, we're not going to do that. The easier way to do this is it increases with molar mass. And you remember that we can get molar mass from the periodic table, right? So fluorine has a lower molar mass than chlorine, bromine, and iodide. Okay? Now we need to talk about our last and the strongest IMF, which is hydrogen bonding. Okay. So this one is really just a special case of dipole-dipole. And in order to get hydrogen bonding, you need a hydrogen bonded to a Falkland. And on this Falkland, you need a lone pair. Okay, so let's go back to like water, because water is a great example of this. Okay, so I have a hydrogen bonded to a Falkland, and there are lone pairs on the water. Okay, so I could draw water like this, and that would be perfectly reasonable. But if I think about water as if I think of, instead of the slashies, I think of just these electrons, okay? The pairs of electrons. And what this means is that this oxygen is really, really electronegative, right? Like there's a lot of negativity on that oxygen. And I guess you could insert your political joke here. I'm just going to stay away from that for now. But and if I do that, if I say that side is very negative, the other side has to be very positive, okay? And it's even more than that, because if I think about this hydrogen sitting there, its electrons are gone, and it doesn't have a neutron. So really, this is just a proton. It's just a proton sitting around empty space. And what would protons really like to find? Well, they'd like to find electrons. And hey, look, water has 2 lone pairs just sitting in an orbital, ready for something positive to come up and interact with them. So the lone pairs of one water molecule can interact. Here's our hydrogen bond. Can interact with the lone pair of electrons. The lone pair of electrons can interact with the protons and the hydrogen of another molecule. And you'll get these huge networks, right? Because like, hey, here's another water just sitting off here, okay? And we could do that, all right? Like there's just a huge network of hydrogen bonds, and these are very, very strong. In fact, they're so strong that they're about half the strength of a covalent bond. What was that, Mr. Ryan? Covalent bond, which is very strong, okay? So hydrogen bonds are strongest, then dipole-dipole, then London dispersion forces. All right, so let's say I ask you, between these 3 compounds, which of them is going to have the highest boiling points and why? Well, in order to answer that question, what you really need to know is, do any of them hydrogen bond, or dipole-dipole, or London dispersion forces? And you kind of go in order from the strongest, which is hydrogen bond, to the weakest, which is London dispersion forces. So hydrogen bonds. Well, in order to have a hydrogen bond, I need a hydrogen bonded to a Falkland. CH4 has a hydrogen, but it's not bonded to a Falkland, it's bonded to a carbon. So there's no, no hydrogen bonds. And no hydrogen bonds in CCl4. There are no hydrogens, and no hydrogen bonds in OF2. Okay, dipole-dipole. Well, in order to do dipole-dipole, I need to know the VSEPR geometries. So why don't you pause the video? This would be a good chance to practice some VSEPR geometries. And why don't you give this a shot? Okay, so CH4 is going to be a tetrahedral. CCl4 is also going to be a tetrahedral. And OF2 is going to be a steric number 4 bent. Okay, so now we got to go through and figure out if we have net dipoles, because that's the only way we can dipole-dipole. So CH4. Well, these carbon-hydrogen bonds, neither one of them is a Falkland, which means that there's no bond dipoles, which means that there's no net dipoles, which means that there's no no dipole-dipole interactions. So CH4 is London dispersion forces only. Okay? Then we go to CCl4. Are there bond dipoles? Why, yes. Yes, they are. They all point outwards. And a tetrahedral geometry, all the base geometries are symmetrical. This one is going to be symmetrical. So the bond dipoles are all going to cancel out. So there's going to be no net dipole. This one was no bond dipoles. This one was no net dipoles, which means no dipole-dipole interaction. Here, OF2, I do have bond dipoles. They point out. Nothing cancels. They're going to add together. The net dipole is going to bisect the angle between those two fluorines, which means that we will get a net dipole, which means that we can dipole-dipole. So here's our net dipole. And if I was going to ask you, like, what was the strength or what was the strongest one, we basically just stop here, right? Because these other two are London dispersion forces only. And this one's dipole-dipole. And as soon as we hit a yes, we actually don't really care about the other ones, because if you have a hydrogen bond that's so much stronger than the other ones, you don't care if it has the other ones because it has a hydrogen bond. And if it has dipole-dipole, you don't care if it can London dispersion force because it can dipole-dipole. So that's why I put a check mark or just a dash down here, because I don't really care. I mean, yes, it has London dispersion forces, but who cares? They're so weak compared to dipole-dipole. So this one is going to have our highest boiling point. Now, if I asked you to make a decision between the other two, well, you know that these are London dispersion forces, and London dispersion forces increase with the molar mass, which means that this one is going to have the second highest boiling point, because it has a greater molar mass. CCl4 has a greater molar mass than CH4, which means it's got more electrons, which means it can do stronger London dispersion forces. So it'll have higher intermolecular forces and thus a higher boiling point. And that's really what you do for these, okay? You need to make VSEPR geometries, and then you just need to go through this table and figure out what you have. And that is all for intermolecular forces.